Now, most of the time, kidney problems are really pretty minor for what we deal with. I'd say maybe about 5% of the total cases that we manage are really kidney-related problems that we have to worry about. So that's why we only spend a little bit of the lecture series in this area. Okay? But 99% of the time, we were talking about cardiovascular, respiratory, ventilation, all that stuff is really what we play off of most of the time. But you still do have to understand a little bit of renal function. So not to make you an expert, but hopefully give you some basis that makes you feel comfortable when you're taking care of people with renal problems, that you don't get overwhelmed by it. Okay? Chapter 6 basically goes into the renal processes for management of sodium, chloride, and water. And really the kidney's main mechanism of water handling is still ultimately sodium balance. Okay? Sodium is by far the best way that water shifts back and forth via osmosis. Okay? So what the overview is of this chapter is going to go over sodium, chloride, and water transport. Okay? What's cool about all these little molecules is they're easily filtered. Okay? So in other words, they get across the glomerulus just fine. Okay? As long as you got hydrostatic pressure, sodium, chloride, and water get across really easily. Okay? But what's really more interesting, I think, is that about 99% of this stuff is reabsorbed. Wow, that's a lot. Okay, you think about it. That means that somebody's doing a lot of heavy lifting, okay, because you're pulling all these molecules back. Now, where does this mostly take place? And the answer is 60% to 65% is in the proximal tubule. And we'll go into the different definitions of that in a minute. So, if you're looking at their reabsorption, is sodium is mainly an active transcellular process driven by sodium-potassium ATP pump. Okay? So, in other words, sodium is still moving across a gradient. Because if you think about it, you're leaving the sodium out of the urine, pulling it back into the cytoplasm and eventually back into the plasma. So it's going up against a gradient. Okay? So as a consequence, it requires a lot of energy. Okay? Reabsorption of chloride is both passive. The reason it's passive is because as you transfer one sodium molecule across, what happens to the cytoplasmic charge? It becomes positive, right? For every one sodium molecule pull across, then it becomes positive by 1 plus charge. To neutralize it, you can pull across a chloride. And that's what it does. Okay? That's why sodium and chloride are always sort of mixing together. They're always kind of friends. One's positive, one's negative. And then you have an active, but is directly or indirectly coupled with a reabsorption of sodium, thus explaining why reabsorption of two ions is usually parallel, which kind of makes it too complicated. But just make it simple. For every sodium molecule pull across, you usually pull a chloride across with it. Reabsorption of water, by the other hand, is by osmosis. Okay? If you pull more salt back, what happens to more water? More water gets pulled back as well. Okay? And as a consequence, if you look at concentrations of the molecules in the urine, they don't really appear to change initially in the proximal tubule. If you look at the sodium concentration and the water concentration, you look at the sodium concentration in the proximal tubules, it appears to be same. And it is. The reason it is, if you want to think about it this way, imagine that you basically filter 100 boxes of sodium and you filter 100 boxes of water. That's what came across the glomerulus. Now, as I walk through the glomerulus into the proximal tubule, 60 boxes of sodium get pulled into the proximal tubule. But because the sodium is such an osmotic driver, it pulls with it 60 boxes of water. So what I'm left with is 40 boxes of sodium and 40 boxes of water, which means my concentration did not change. Okay? But I still moved 60% of the molecules already across. And that's really hard for a student to understand until somebody sort of points that out. If you start looking at it that way, it makes sense. Kidneys do no longer overwhelm you with this concept. Just think of it as a number of boxes that are moving at every single section. So let's look at first the sodium reabsorption. What we'll show you is this picture here, and we'll come back to that in a minute. Okay, is that I'll show you first in writing, and then I'll show you for the people who like visual, which is what I tend to do. I tend to draw my cells and show what they're doing. Okay. If you're looking at sodium processes, you have a sodium nutrient symport. Okay. What's a nutrient symport mean? that's going to things like amino acids or sugars to come with it. Okay? So sometimes you can pull the molecules across, and you're pulling two of them at the same time. You also have a sodium phosphate symport, because if it makes sense, for every sodium you're pulling across, you're pulling phosphate across. Then you have sodium sulfate, sodium hydrogen, and just specific sodium channels. And that's on the luminal side. That's where the urine's at. That's what's pulling the molecules across into the cytoplasm. Okay? On the basolateral membrane transport side, that means that's the side that's attached to where the basement membrane is at, which is right next to the blood vessel. Okay? So ultimately, the only way to get sodium out of the cell is it's got to get pumped out into the plasma. And that's where your energy sources are. Okay? That's where the energy is going to consume it, because that's one that's going to be really pushing it up the gradient. What you're doing, basically, is the following. Okay? If I have, I'm going to make it simple. Okay? Imagine that you have 100 boxes of sodium crossing into the urine. Okay? And you have 100 molecules of water, 100 boxes of water. Okay? That's in the urine. As it's walking by, it sees the proximal cell next to it. And in the proximal cell, there's actually 5 boxes of sodium. So which way is the sodium going to go? It's going to go down the gradient, right? So the movement of the sodium in the urine into the cytoplasm of the cell is actually mostly passive. Okay, does that make sense? But here's where the but part comes, and this is where the energy requirements are. On the other side, on the basolateral side, that's pointing towards the blood, the concentration out there is 140 boxes of sodium. And now I have maybe 10 boxes of sodium in here. How do I get it up the hill like that? That means I have to push it out. I have to shove the box into an energy processor and push it out. And that's why all the energy utilizers are on the basolateral side of it. Okay? You're creating a sink, which is the cytoplasm, to pull the sodium in, but then you're pushing it out against a gradient into the plasma. Okay? You also have in this system on that side is you have the sodium bicarbonate symporter, okay, which pulls bicarbonate, which is going definitely down a gradient, which is good. At the same time, helps pull sodium across with it. So this is your friend, okay. In different books, you got to be very careful what it's telling you. You know, I wish I had yellow in here, but of course we don't have yellow. So instead, my urine's going to be green. Look at that, you know. So we're going to make our little urine here green. Okay, so this is our urine. And over here is going to be the bloods. Okay? So if you look at this carefully, you can see that your sodium bicarbonate system is right here. Okay, that's one. But these are all the symporters I was telling you about. This is the sodium nutrient symporter, so it's got glucose, amino acids, any other kind of nutrient will come across. Okay, sodium phosphate. Okay, then you have the antiport system, which is sodium coming in for a hydrogen going out. Okay, and that's important for acid-base balance because the urine really wants to get rid of the acid. So hydrogen ion tends to come out in the proximal tubule. Okay, and you can see also the chloride coming across back in, and then you have your main mechanisms here. Now, this system here, right here, requires ATP. Okay, that's the sodium-potassium ATP pump. Okay, just like a sodium-potassium ATP pump in any other cell, but these guys work a lot harder. Okay, they're pulling a lot of sodium back into the bloodstream. Okay? Does that make sense? Okay, so be very careful about when you look at drawings, make sure that you got them pointed in the right direction. Always put your urine on one side so you know which one's the luminal side, and then look at your basolateral side, put the red side. That's where the plasma's going to be at. That's where the blood's going to be moving at. If you look at a chloride reabsorption, it's basically trying to maintain electrical neutrality. So anytime you pull in a cation into the cytoplasm, such as sodium, potassium, things like calcium or magnesium, then you're going to pull an equivalent amount of chloride. So if I tell you that you're pulling across 1 calcium molecules, how many chloride molecules am I pulling across? Calcium has what charge? 2 plus. So how many chlorides are going to pull across? 2. If I pull 1 potassium, how much chloride am I going to pull across? 1, because there's only 1 charge. Sodium has also 1 charge. So it's going to try to maintain electrical neutrality for you. Okay? There's other anions that also will help you do this, which is bicarbonate, carbonic acid, bicarbonate, which is HCO3, sulfate, phosphate, and proteins also will help maintain electrical neutrality. Okay? So most of reabsorption of negative ions tends to be passive. It tends to follow where sodium is going in simply to try to maintain electrical charge to be equal. Okay? The critical step, transport step, is lumen to cell. Okay? You get paracellular absorption, which is a complicated parallel set of sodium and hydrogen and chloride-based antiporters, which are linked with your sodium reabsorption, which basically what their book is trying to say there is that for every sodium molecule that you're bringing in, you're going to pull in a chloride with it. Okay? And it will require active transport from the lumen to the cell. Okay? Cell to serosa is passive via electrical chemical gradients, okay, which are something that we'll show you in a minute. So when you look at sodium reabsorption, okay, when it's being pulled back in, you're creating a gradient, okay, by causing the sodium, the cytoplasmic concentration of a proximal tubule to be very low in sodium. So as a consequence, it pulls the sodium in to the cell from the urine. Okay, with it, it will pull water first. Okay, with the water and the sodium coming in, then it'll cause the lumen to become more positive. Okay, in other words, it's becoming more charged. And as a consequence, the actual chloride will move into the cell. So you get passive chloride reabsorption. Okay? If you look at the other thing that water will do is that it increases the luminal chloride concentration, and it also increases the luminal urea concentration, which helps push urea into the proximal cells as well. Remember, 50% of what urea is actually filtered, it's filtered, is eventually excreted. But a big percentage of that initially is reabsorbed. If you look at water reabsorption, about 65% of reabsorption is in the proximal tubules, simply because it follows sodium. Okay? So when people tell you, and this is a trick question, a trick question on test on boards and C exams, they'll say to you, well, which area has the most important for reabsorption of water? And it's simple. It's proximal tubule. The reason that's sort of a trick question is because almost everybody thinks of what as being the most important for water transport? The loop of Henle. Okay, but the loop of Henle only accounts for 10% of the movement of water. So really, it's really a minor player. The reason it becomes such a major player in our thinking process is because we can give people loop diuretics, which are poisoners of this pathway. And as a consequence, you will get a lot more urine formation. Okay? But in reality, it's not as potent. If you had a way to basically take the proximal tubules and poison them so they couldn't reabsorb water, you couldn't imagine your diuresis you'd have. It'd be coming out by the gallons. Okay? So be aware of that. Okay? So 65% is pulled in by the proximal tubules, 10% is by the loop of Henle. And it works in a different system. Okay? It's different than sodium in the descending limb of loop of Henle. Sodium reabsorption occurs in the distal convoluted tubule but not water due to the tight junction. So and I'll show you the drawings of this in a minute, how different portions of the loop of Henle, when they convert from one area to the next, will change their permeability to water. Okay? Water transport is always passive, and it occurs via osmosis. And it tends to follow where the higher electrolyte concentrations are at. So in other words, usually wherever salt is high, that's where water will go. As the active systems pump ions into the interstitium, it increases the salt concentration inside the interstitium, which is the area around the loop of Henle. Okay? So and we'll talk about that in a lot of detail. We'll talk about how the system gets charged up, and then how water will get pulled out of the tubule and concentrate the urine as you go down the loop of Henle. What's interesting about the loops, about the actual nephron, is that it has a variable tightness to water. Okay? In the proximal tubules, It's pretty loose in the sense that it allows water to come across based on sodium without too much of a problem. Okay? If you look at the descending loop of Henle, it's also very permeable to water. Okay? It's mostly impermeable to sodium, but it's very permeable to water. So it allows water molecules to cross very easily. That's considered the concentrating limb. Okay? But as you come up the loop of Henle, the actual cells become super tight. They become basically impermeable to the loss of water. And as a consequence, what you end up happening as you come up the actual ascending loop of Henle, you will start getting dilution of the urine. Okay? And those words are kind of tricky. What you have to remember is you have to think of the number of boxes, the box analogy we talked about before. Okay? If you look at the permeability of the distal convoluted tubule and into the cortical collecting duct, you can actually change the permeability of water. If I make something more permeable to water, what happens to its reabsorption? In other words, if I give you an antidiuretic hormone, it works at the collecting ducts. They don't work in the loops of Henle. They don't work in the proximal tubule. They actually increase the permeability to water of the tubule. So that means when the water gets into that section, it gets pulled back into the cells, back into the interstitium. Okay, so what happens to the urine? It concentrates. Okay, so be very careful about the wording. Okay, if on the other hand I don't give you any antidiuretic hormone, then the cells in the cortical collecting duct become almost impermeable to water. So the water that's in the urine cannot get out. And as a consequence, you will form a very dilute urine. Okay. Reabsorption and secretion along the different parts of the nephron. Depends on the degree of reabsorption of a solute. Okay. The best way I can describe this to you is, again, looking at it in the box analogy. Okay? I keep it simple in my mind and keep it at 100. The reason I like the 100 boxes is because now I can play it with percentages. Keeps it kind of simple in my mind. Okay? Is it 100? No. And if somebody comes back and sends a physiology that's into nephrology, he'll basically beat me with a stick. Okay? Because you say, well, it's not accurate. And I agree, it's not accurate. But it gives you an analogy, and that's what I want you to get across. I want you to get an understanding of what the molecules are doing. So the best way to look at it is, at least the way I think about it, it makes it easier for me to train you guys, is think about sodium as walking across the glomerulus. 100 boxes with 100 boxes of water. By the time it hits the proximal tubules, it pulls 60 boxes of water with 60 boxes of sodium. Okay, so what's happened to the concentration of my urine at that point? It's unchanged. But there's a lot less of it. Okay, there's 60 boxes less of each. As I go down the descending loop of Henle, okay, what I first start losing at that point is the sodium doesn't move. But water gets pulled out. Water starts pouring out because the descending loop of Henle is permeable to water. And the water is going into the interstitial space, which is full of sodium. Okay? So this is considered the concentrating effect. As I go down the loop of Henle, the more concentrated the urine forms. If I want super concentrated urine, and I want to basically be peeing out sand, which is what a desert rat does, believe it or not. Desert rats don't lose any, so it's called the desert mouse, not really a rat. Rats are ugly. Okay? Again, I'm showing bias. I saw a big rat over here the other day. He ran across from me and almost ran me over. The sucker was so big. So just be careful early in the morning. You might see a few rats around here. Anyways, as I was saying, the desert mouse concentrates its urine so much that it actually drops dust into its cloaca, okay, which it doesn't have a bladder. There's no reason to. So it deposits its urine as dust particles, which is rather interesting. So that's a metabolic waste product. Human beings don't do that, of course. They have to maintain a certain amount of solute, okay, or solvent. By the time if you get into a really long loop of Henle, the more concentrated urine gets by the bottom. Okay, as you come back up, then the number of boxes of water don't change. But what ends up happening is you start pumping out boxes of sodium. So the actual number of boxes at the bottom, you're saying maybe about 30 boxes of sodium, and there's 10 boxes of water. As you come up, then you're losing 25 boxes of sodium, but not changing the water. So the consequence, you're down to 15 boxes of sodium and around 10 boxes of water. So it makes the sodium appear to be concentrating. That's why it's called a concentrating effect. But what you need to think in your mind is, what's it doing? It's moving these molecules out. It's basically reabsorbing them eventually back into the bloodstream. So what your body really does is it plays with the last 10%. But whatever you filter, it's really playing with the last 10% to determine the quality of the urine that you end up having. Okay, so it's really a small percentage. It's really what it does. Okay. So the greater the solute reabsorption, the more dilute the urine concentration. Okay. The most important solute, of course, is sodium because it drives the system. It creates what's called a transtubular osmolality difference, which favors reabsorption of water by osmosis. In turn, water reabsorption concentrates many luminal substances, including chloride and urea, which then helps favor their reabsorption by diffusion. Okay, so it has a double effect. You achieve this reabsorption from many organic nutrients, phosphate, sulfate, and by cotransfers across the luminal surface, and achieves secretion of hydrogen ion by a countercurrent cross system, where you begin to waste hydrogen ions into the urine, which is what you want to do. And in the process, it uses there's two areas where you have high concentrations of carbonic anhydrates: kidney and your red blood cells. Your red blood cells, of course, are converting CO2 into water plus CO2 into carbonic acid, which eventually forms hydrogen ion and bicarb, and the bicarb goes to your plasma. The same thing happens here, in a sense it's the same kind of enzyme, but what it's doing is it's taking hydrogen ions and wasting it into urine and pushing bicarb back into your plasma to try to maintain the buffering capacity of your bloodstream. Okay, so the kidney is very important in doing this. And if you lose kidney function, what happens to the person's acidosis? It goes up. They become basically chronic metabolic acidotic patients. Okay. Again, this is my favorite picture. So because of this, I think you need to memorize it. Okay. I think it's a way of clearly defining what's occurring at the kidney. So let's walk in through here. Okay, let's do the sodium. Let's keep it simple and keep it to sodium. Okay. And we're going to do the box analogy. We're going to say, let's see, 1, 2, 3, 4, 5. Okay, so that's 1, 2, 3, 4, 5. Okay, so we're going to say each box is 10 here, okay? And that's your water, and this is your sodium. Man, it sounded like a dog shaking. Okay. Whose bracelet was that? Was that yours? That's cute. Anyways, you can see I'm getting punchy too. I've been at work since 6 o'clock this morning. It's been kind of an interesting day. So, if you look at the concentration of sodium and water underneath it, you have basically I made it 10 boxes each. So each one is basically 10%. Okay? By the time you finish the proximal tubule, what you've gone from this is basically eliminated this. So now this person at this point is down to 4 boxes of water and 4 boxes of sodium. Okay? So the concentration itself does not seem to appear to change. Right. Okay? Now as I go into the loop of Henle, what I do down here is that I lose 2 more boxes of blues. And so by the time I get to this area here, at the bottom of the loop of Henle, I've got still 4 of sodium, okay, but I have only 2 of water left. So what does that look like to you? It's called a concentrating effect. but I'm still moving more molecules across. That's what I sort of want you to get. It's part of the process of understanding how the kidney function is. Where is the stuff moving around to? Then, when you come up the loop of Henle, okay, when it turns a corner, all of a sudden it appears to be diluting the urine. Okay? And the way it's doing this is now you're going to lose 3 boxes of sodium, and you're going to end up at the end having 1 box of sodium, and you're going to have 2 boxes of water. But look how many, I started with 10 boxes of each. I'm down to 2 boxes of water and 1 box of sodium. So 10% of sodium and 20% water left. It's not a lot, think about it. And then the end process, the distal tubule and the collecting tubule, will make the final determination of what I should do with that urine. If I am dehydrated, what do you think is going to happen? I'm going to release lots of ADH into my bloodstream. The ADH is going to go into the distal convoluted tubule and the collecting tubule and tell it, hey, suck up all the water back. So what I will do is I'll basically pull all this back, and now I have a super concentrated urine. I still have a little bit of sodium in it, but not much. Okay, but it'll be very concentrated urine. On the other hand, if I have a person who's overhydrated and ADH has basically gone to 0, then those last 2 boxes don't leave. So what I end up having is a very clear urine. You've all seen this in yourselves. You've seen it where you actually are very dehydrated and your urine's turned really dark yellow. Not green, sorry. St. Patrick's Day, yeah. Okay? I hope you're not green. Or if you've drank a lot of fluids, a lot of free water, then you start noticing that your urine is almost like the water you just drank, and because you're basically overflooding your system. And that's all it is. Does that make sense? Okay. Let's look at the different components. The proximal tubular reabsorption is where 65% of sodium and water is reabsorbed, and these two are what's called an isoosmotic volume reabsorption. So if you have to say the number of boxes, it'll be 65 boxes of sodium and 65 boxes of water. It has a very high capacity for active and passive transport in this system. And the reason these cells are so capable of doing this in this area is because if you look at them, they're cuboidal cells. They're specialized cells that their job simply is to pull back molecules. So they have a huge amount of ATP utilization. Okay? The other thing they're able to do in the proximal tubules, they're able also to secrete things like organic acids and bases. Okay? The anions that are pulled in to maintain electrical neutrality are also being pulled as a consequence when the sodium gets pulled, things like bicarbonate, organic nutrients, phosphate, and chloride. Okay? And if you look at osmotic diuretics, where they actually work, they work here. Okay? Osmotic diuretics poison the proximal tubular system by preventing either sodium reabsorption or by putting enough osmotic load that water doesn't follow where the salt's going. So when I give somebody mannitol, that's an osmotic diuretic. You've all seen how powerful mannitol can be. Okay? You give somebody 25 grams of mannitol, and all of a sudden he's putting out 2 to 3 liters of urine. Okay? And that's simply because you're poisoning the proximal tubule system from reabsorbing the water. And the water will stay on the area that has high osmolality. And in this case, it would be from mannitol. Now, the loop of Henle can be broken down into 3 parts. Okay, so you went from the proximal tubule, all of a sudden now you went into the loop of Henle, which goes downwards and then comes back up. Okay? So the loop of Henle is broken down into a thin section, thin descending, and you have a thin ascending, and then it becomes a thick ascending. Okay? The thick ascending, why is it thick? It's because the cells in here are cuboidal. So what does that mean to you? That's where a lot of work's going to be done to transfer cations or electrolytes. Okay? If you make something thin, what are you really moving? Water. You're just basically moving something that is very small and easily permeable. Okay? If you look at the thin descending portion, this area here is highly permeable to water. Highly permeable to water. Okay? On the other hand, the ascending portion becomes impermeable to water. It does not let water come across. If you look at the boxes of numbers of water molecules that you're moving across, you've already pulled off 65 in the proximal tubule. Normally you'll pull another 20% by the time you hit the bottom of the loop of Henle, if you have a long loop of Henle. If you have a short loop of Henle, it could be as low as 10%. But most of the time when we're talking about these examples is a long form loop of Henle, so it's around 20%. So now you've removed 85 boxes of water, and you're left with 15. Okay? Your thin ascending portion is impermeable to water, and as a consequence, as you begin to go up, you begin to able to concentrate the urine, because the water is not going to go, Yes, impermeable water is concentrating the urine, okay, because it can't get rid of the water, okay. Now the thick ascending portion, okay, becomes a diluting segment. The reason it's a diluting segment is this is where you're beginning to pump out the electrolytes. These are where you begin to lose the sodiums out. But what happens to water inside here? It's impermeable to water. Okay, it's still impermeable to water. Okay. The active transport mechanisms here are the sodium-potassium pumps, and they're responsible for about 25% further reabsorption of sodium. And they're mediated basically by sodium chloride, potassium co-transport systems. And still, but by far the most important thing that you're moving across is sodium. Okay? The loop diuretics, what they do is they poison you here. So the loop diuretics does not inhibit the descending portion or the thin ascending portion. It actually inhibits the diluting section, which is the thick ascending portion of the loop of Henle. That's where the loop diuretics work. Okay? What they do is they inhibit the movement of sodium into the interstitial space, and it kills the gradient. And as a consequence, the person begins to form very dilute forms of urine. Okay, again, this is to show you the different cells, how they look physically different. Okay? And just by looking at their physical structure, you can tell if something is going to be, it's going to filter water very easily or not. Okay? If you think about this is pretty thick. This is not going to be very permeable to letting water exchange out, and it doesn't. So in the thick ascending loop of Henle, you're really not moving water. All you're doing in this situation is you're moving electrolytes, mostly sodium. What they are showing you again is be careful when some of these drawings, and I'm sorry, I took them out of two different books, which maybe one of these days I had the patience to sit down and basically redraw them myself. I think it would make it more clear sometimes. But what you're seeing here is that this is flipped. This is going to be the luminal side, and this is where the blood side's at. Okay? So when you're looking at the thick ascending portion of the loop of Henle, what you're doing is you're producing a gradient with energy, pulling sodium across the cell. So the sodium concentration is low inside the cytoplasm, which drives the SYM-port, the anti-port system for hydrogen going out. Hydrogen is going out for every sodium going in. Okay? You also have this system, which is pretty important, actually the most important of the two, which is a sodium chloride potassium co-transport mechanism. Okay? For every sodium that's coming in, you're bringing one potassium in, and you're also pulling in two chlorides. It kind of makes sense. It maintains electrical neutrality. Okay? And this is where the actual, right here, is what the loop diuretics inhibit. Okay, so loop diuretics basically poison that section, and then as a consequence, you can't pull sodium back into the cell. Again, this is the same picture, but in a different book. Okay, and this is going to be the luminal side here. The reason I like this picture is because it showed you where the actual loop diuretic works, which is the same system I was trying to show you before. Okay, the chloride, sodium, potassium syn-porter. Okay. When you get further down, further along, you get into the next portion. So what you should do, or we should try to do to help yourself learn this material, is I would take basically a table and say, okay, glomerulus, proximal tubule, descending loop of Henle, ascending thickened loop of Henle, ascending thick loop of Henle, distal convoluted duct, and cortical collecting ducts. Okay, so that's how it's separated out. Okay, and then say which area is doing what each area is doing. I got a thing that'll help you later on. But the first section is filtration. The next thing is reabsorption, which is in the proximal tubule, 65%. Then you're going to thin limb of Henle. Then you go into the thick ascending portion of Henle and start describing it. The next one in this table would be the distal convoluted tubule. And the distal convoluted tubule is basically a specialized cell that is cuboidal again. And what does that mean? It's going to move ions. Okay, it's going to be very selective about its movement of ions. And it's also going to be very impermeable to water. Okay, so it's a tight junction system. So everything after the loop, at the ascending loop of Henle, you're looking at a basically tight system until you have a hormone that changes that. Okay? But in the distal convoluted tubule, what's interesting about it is that it runs very close to what's called the juxtaglomerular complex. Okay, it's actually part of the juxtaglomerular complex. The way I describe this is like tasting, it's like wine tasting. Okay? Your urine has certain qualities to it. And to make a good urine, good quality urine, you have to have something that senses the taste and figures out how good it is. One of the things that we used to freak out the first year medical students was, I don't know if you've ever done this. This is kind of a cool thing to do. Actually, it's kind of cruel, but it's kind of funny. We would have a patient in the ICU, which of course was one of the residents, and we would put like a fake Foley attached to him, and then we'd fill up the urimeter with apple juice. And apple juice looks just like urine. I'm sorry, it's kind of cool. So we would tell the students, we'd give them this whole discussion about how urine is very important, that you have to sort of, there's a good quality urine, there's a bad quality urine. And so one of us would go up to the urimeter, open it up, pour it into a little cup, and then we'd taste it. And then you see people start to hurl. It's great. It was really kind of cool. And we looked at it and said, see, you need to taste it. And then we'd give it to the next student. And of course, nobody wanted to taste urine. Okay? It was apple juice. Okay? I think one of these days, I was afraid, and I made sure that the urimeter, I kept an eye on it, because I was afraid that some medical student would finally get wise and switch it and put a little urine in it for us, and really put a really bad day for us. But we never got caught that way. So in essence, and actually, if you read back in time, doctors did taste urine. They actually used to do that. They would tell you that your urine tasted sweet. And what was the diagnosis for? Diabetes. Okay? When they would actually smell or taste your urine and it would taste sweet, that was your diagnosis, was that you had diabetes. Those must have been incredibly tough people. Okay? Things have changed a little bit. Okay? Yeah. That being said, the distal convoluted tubule basically acts as a taster. It really determines the quality of the urine. And there's cells that are right next to that area that basically alter urine blood flow and will change the quality of the urine that you form. Okay? So it's kind of important. If you're looking at what is reabsorbed mostly, it's a sodium chloride syn-porter. That's working here. So that's the most important. The things that make this area more permeable to water is ADH. So ADH will affect the actual distal convoluted tubule as well as the cortical collecting duct. When you cause the person to secrete ADH, that person will reabsorb more water. and make the urine more concentrated. Anti-diuresis. Okay? Normally, if you don't have any ADH, this area is basically impermeable to water. Okay, so only when ADH is being secreted does the distal convoluted tubule open up and allow more water to be pulled back in. Okay? The other area that's important about this is where thiazide diuretics work. And you think about it, which one's going to be more powerful? If you had to put a diuretic, where would you put your biggest bang for the buck? Proximal tubule. Okay? Because if I can inhibit any reabsorption there, it's going to give me a much more bang of urine out. So thiazide diuretics are weak. The reason that they're weak is because there's only about 15% of the actual urine that's been filtered, it reaches there. So you're really not going to affect the water balance that fast. Thiazide diuretics don't work like loops diuretics where they begin to pour urine out of them. They've never seen that happen. It's very kind of gradual. Okay? It doesn't mean it doesn't work, it just works very slowly. The other thing that's important about the distal convoluted tubule is it's considered the diluting segment. The reason it's diluting segment is because it's pulling electrolytes without you normally pulling water back in with it. Okay, and it usually pulls sodium and chloride back with it first. And it's also a very important site for control of calcium homeostasis. So this is the, again, make sure that you got the luminal side. So I'll do my green urine for St. Patrick's Day. And I'll put my serosal interstitial. This is the distal convoluted tubule. What's important about this is that here, the sodium chloride pump is where the thiazide diuretics inhibit, okay, which kills this process. And normally you have sodium and calcium being pulled back in from the urine into the cell, which then gets pulled back into the plasma, and that's regulated by, to a certain degree, by parathyroid hormone. So parathyroid hormone is very important to uptake calcium back into the system here and maintain your calcium levels in your bloodstream. Eventually what you end up getting is that you'll secrete calcium back into the plasma, and you'll have an active pump system, the sodium potassium ATP pump, where you basically establish this gradient. So this is going to require a lot of workload again. Okay? So the areas that are most sensitive to ATN are going to be proximal tubule, number one. Second one is distal convoluted tubule. Those are the two areas that are going to get hit when you don't give enough oxygen to the tissue. Now, when you get further down, you can get into crazy different kinds of cells and to specialized cells in the distal convoluted tubule. It's called the late distal. And about 70% of the cells in that area are called principal cells. Okay? Principal cells. They're really kind of cool. I like principal cells because what they do is they reabsorb sodium and secrete potassium, which is good because that means you can waste potassium, which is a waste product of metabolism. And it also does something else for you, okay, which is it retains, it will help retain water using ADH through that system. But aldosterone basically inhibits sodium reabsorption here. And as a consequence, that person will begin to diurese in that situation. So aldosterone works mostly in principal cells. If you look at the intercalated cells, okay, the intercalated cells, their job is to basically get rid of hydrogen ions. Okay. Now, how do you remember which cell is doing what? And the way I remember it is I remember ions for intercalated, for intercalated for ions, and the most important ion that you want to get rid of is usually hydrogen. Okay, it's a cation, of course, but it is a form of ion. And intercalated cells are very avid, and they have high amounts of carbonic anhydrase in them. Okay, and they pump out hydrogen at the good thing of pumping bicarb back into the bloodstream. Okay, so the distal convoluted and the cortical collecting tubules are very important in trying to maintain your your bicarbonate balance in your bloodstream. Okay? It also reabsorbs potassium ions and plays a very key role in acid-base balance. So I for ion control or intercalated cells. That's really what it's going to do. Okay? The other cell that's similar to that, okay, this is the intercalated cell. It shows you how the carbonic anhydrase, this is the luminal side, okay, So this is another one. Sorry, this is the normal. This is the normal intercalated cell. The lumen here is the urine, okay, and it's basically wasting hydrogen ions out this way. And then you can take the cell and literally flip it, and that's what this picture shows you. This cell is flipping that. In this situation, you're actually now doing what with bicarb? You're wasting it, okay? And which one I have to say, which one has more amounts? The intercalated cells. There's a lot more of them. Because the normal process of metabolism is to produce hydrogen ions. So it kind of makes sense that you need to waste them. So you would have a lot more intercalated cells in your kidney under normal circumstances. But at the same time, you have situations where you do form excessive amounts of bicarb sometimes, okay? And then the body's got to get rid of it. But it's really a very small percentage of the distal convoluted tubule and the cortical collecting ducts, the number of cells that actually are able to do that. All they've done is the cell, I mean, the kidney's not anything fancy. All it did is it took a cell and just flipped it. That's all it did, okay? And normally these guys are asleep. I'd say about 90% of your lifetime, these cells don't do anything. They sort of sit there and just sort of job of just sitting there waiting for the day that they need to do something, okay? These are really like your firemen, you know, where they're doing nothing most of the time, but when you do definitely need them, hey, you want them to be around, okay? So when you become alkalotic, these are the guys going to save your butt, okay? Now, there's a name for them. I can't remember the name of them right now. Let's see if I can remember. It's called a type B intercalated cell, okay? And it's got another name for it. I can't remember right now, but the type B. The type A is the intercalated cell that's responsible for acid movement. Type B is for base. That's how I remember it, okay? A for acid, which is your secreting acid. B for base removal, okay, which is type B. As we go on to talk about the next part, which is permeability of water, okay, this can sometimes confuse people, so I'm going to make sure that we go through it slowly and make sure that we understand this properly, okay? And if once you get this, it's not difficult. Just sometimes it confuses people, the wording. And that's what catches people on the test. That's what matters. And you got to make sure that you get the wording straight in your mind. When you're talking about permeability, okay, I want you to imagine that you're sitting in the urine. You're traveling in the urine. I know, you're in the yellow river, okay? Okay, as you're traveling along, the doors beside you are closed. That's a normal process. When you get into the distal tubule and the cortical collecting duct, the river is running with all the doors next to it are closed. Okay? And if you continue that way, then you will form a very dilute urine. To open the doors, to let me out, in other words, let the water out, okay, I have to add something to open the doors. I have to have a key to open the doors. The key that opens the doors mostly is ADH, antidiuretic hormone, okay? And what it does basically is it opens the doors to let water go out from the urine. And that's what we call it, making it permeable. Okay, big word. You know, instead, just think of it as a door. When you add ADH, you make the cells more permeable, which means that more water will leave the urine. Okay, will escape. Okay, if on the other hand, if I make the system impermeable by leaving the doors closed, then the urine will become dilute. Okay? So if you have very high ADH, it makes the tubules permeable to water, and more water is thus absorbed, making the urine much more concentrated. If you have low ADH, it causes the system to have low permeability to water, and the more water is diluted and urinated out, and works basically on the principal cells. Okay? ADH, of course, has a special wording when you give it in high doses as vasopressin. Okay? Vasopressin has two effects. It's an intense vasoconstrictor to the point that actually will basically knock out urine blood supply, okay, which is a problem with it. Okay? But under normal circumstances, when you give ADH, on lower doses or higher end doses, it's really not affecting blood supply. It's really affecting the movement of water at the distal and the cortical collecting ducts. Okay? And it's basically not permeable to urea as well. If you look at the medullary collecting ducts, which is now you're further down in the medullary area, they account for less than 10% of the water or sodium reabsorption. So this is the last bit of your urine. Okay? And this area is also affected or altered by ADH. And so if I make the area more permeable, it concentrates my urine. If I use less ADH, then it becomes less impermeable to water, and as a consequence, it becomes a more dilute urine. What's interesting about this is in the medullary collecting duct, you do have permeability to urea. That's interesting. That means in the cortical collecting area, urea doesn't cross. But for some reason, in the medullary area, it crosses. And you have to think to yourself, well, what makes urea such a special molecule then? Why is the kidney being very specific about how it handles urea? Why does it wait till the last second to make it permeable? And the answer is that medullary collecting ducts are right next to these guys. They're right next to the loop of Henle. Now, you're never going to see this written in a book. And, well, maybe in the future, but not right now, okay? What I want you to think of is that the loops of Henle are inside like a bucket, okay? So it's like I have this bucket, and inside this bucket, I can fill it with different things. And then when I put in my tubes inside of it, I can make the tubes act differently, okay? And what's really cool about it, as you think about it that way, where is my urea going to be in really high concentrations in this bucket? Because at the top of the bucket, there's no urea coming out of it. But urea is heavy, and it tends to fall. It tends to stay in high concentrations once it stays there. So urea is pumped into the bottom of my bucket. Okay? So my bottom of my bucket now is full of concentrated urea. What's that going to help me with the ducts? If I make something super concentrated, what's water going to want to do? It wants to dilute it out. And that's what urea does. There's two things that help pull water across the loop of Henle. One is high sodium concentrations on the bucket, and the other is high urea concentrations. So urea is actually a pretty important osmotic driver to pull water out. Okay? The longer the loop of Henle, the more urea I can deposit into the bucket. So the more concentrated the urine can become. Okay, so if I'm looking at a desert mouse, he has very, very thick, very long loops of Henle, but he also has very high concentrations of urea inside his interstitial bucket. Okay? I don't know if you've ever been in the desert. You can actually smell the rat feces. You can smell it. Okay? You can actually smell the urea in it. Okay, so it's actually very heavily concentrated. So let's look at our different guys here. This is the major transport pathways in the medullary collecting duct. Okay? This is the luminal side, this is where the urine's at. So urea is able to cross over, which is definitely unique. To pull urea across, it actually allows ammonium to form inside the urine, which gives you that characteristic urine smell, which is ammonium smelling, which is part of the medullary collecting system. It helps remove additional ammonium. Okay? It also is able to secrete hydrogen ions very effectively and also pull potassium back in this way as well. is a potassium, it is a sodium-potassium pump requirement. So this is a going down gradient, but it requires active transport to be able to do this. And also the medullary collecting duct system is important for forming bicarbonate through carbonic anhydrase. Okay. So let's look at the urine concentration, the medullary osmotic gradient. This is by far one of the hardest things to explain to people. Okay? So I'm going to try to keep it to a certain, not go crazy with all the details. Okay? But I want you to sort of understand that if you look at the proximal tubule, there's no concentrating effect normally. Okay? In the proximal tubule, you're just moving the same number of boxes in of solute and solvent. Okay? So if we're looking at the examples with water and sodium, we're pulling 65 boxes back in the proximal tubule of sodium, and we're pulling 65 boxes of your water. But as you travel downstream, okay, you will notice that water begins to leave. Okay? This water leaves in higher and higher quantities till eventually you have a very concentrated urine by the bottom of the loop of Henle. Okay? Now, the big question is, and it was for a very, very long time, what's doing this? What is causing this? How does this take place? And the best way that I can explain it is that if you take this drawing and change it just a little bit, let's modify it. So now I'm going to put in here a bucket. Okay? Now, some of you don't drink, I know, but I think most of you know what a Long Island iced tea looks like. It's a great way to get a woman drunk really quick. Okay? Sorry, but I've seen my wife get hit with it one time, and she never drank it again. And I was getting worried because I wasn't married at that point, and my wife says, "I can't go home like this." I'm going, "Yeah, you can." So we sort of walked around for several hours. But what Long Island iced tea is they have different densities of alcohol. And you can actually see them. They form this very pretty layer. Okay? The bucket that you have inside your interstitial space is the same thing. It has different densities of solutes that are being dumped in there. Okay? They're not quite alcohol-based, they're different based. They're based on chloride, sodium, and urea concentrations. If I were to take urea, let's make it like a light green color, okay? Then my urea would be in very high concentrations on the bottom. Okay, so that would be my first portion of my Long Island iced tea. The next one would be higher concentration of sodium. That would form here. And as it's coming up, it would be a lower concentration of sodium. And eventually, I get back up here, I have the lowest concentration of sodium. And the question is, why does it do that? Well, here's why. Okay? The loop of Henle, okay, in the first portion of it with the thin descending portion of it, is totally impermeable to electrolytes. It will not allow electrolytes to move across, but it will allow water to cross over. And how you charge this chamber, how you charge this bucket, is through the right here, the thick ascending loop of Henle. The thick ascending loop of Henle pours sodium into this bucket and doesn't allow any water really to come out. So it concentrates the bucket. So what you end up having when you're finished really charging it all up is you get this gradient effect with urea being at highest in the bottom, followed by higher concentration of sodium, higher, and then it gets lower and lower and lower, eventually till you get to the top. And that produces the osmotic gradient. Okay? Now, how that's maintained is rather interesting, of course, because if you pour a bunch of sodium out, what eventually will happen? It'll equilibrate, right? And what happens when water starts pouring out of the loop of Henle? It's going to eventually dilute it out, right? Well, if you give somebody a loop diuretic and you inhibit this, if you give a loop diuretic and inhibit it right there, what happens to my gradient? You still have a little bit of urea, but my gradient is killed. And because of that, I start forming very dilute urine. I cannot no longer concentrate the urine. As it goes down the loop of Henle, it has no more gradient, so water doesn't leave. So now instead of having 10 boxes left, by the time I'm going up the ascending loop of Henle, I'm at not 30 to 40 boxes of water still left. Okay, and it forms a very dilute urine as a consequence. Okay? Now, what also maintains this gradient, what keeps it going, is a counter-current blood supply. Okay? Counter-current. So when urine is going in one direction, the blood supply around the bucket is going in the opposite direction. Why would that be important? Well, because if you look at the blood concentration in here, it's going to be, sodium's going to pour out into here. Okay, so the sodium concentration is going to begin to jump up on this side, right? And by the time it comes onto this side, what's going to want to do? It pulls the water this way. That's called the counter-current system. Okay? One side is loading up with sodium, which is a plasma, very similar to the bucket. But by the time it comes to the opposite side, the water now is freely diluting everything out, and it now gets pulled into the plasma to dilute my plasma back to its original concentration. And it keeps the system charged. You don't lose it. Okay? So it's 3 systems in place. 1, urea. 2, sodium-potassium pumps, pumping sodium into the bucket. And 3, the countercurrent system, going in opposite directions from urine flow. What are the blood vessels called to do this? What are the blood vessels called that do this? Vasa recta, the straight tubes. Okay, because they're similar in tubes. They're straight tubes. They come along, but they're going in opposite directions. Blood flow is going one way. Urine flow is going the opposite way. So they're counter current. Yes, sir. And what? They're different. The efferent eventually binds to the vasa recta. But if you look at the blood vessel diameter, the blood vessel of the efferent and the afferent arteriole have smooth muscle, and they're thick. They don't allow molecules to move across very well. The vasa recta, on the other hand, looks like a capillary. So it's thin-walled, and it allows easy transfer of molecules across. That's why it's able to charge up the sodium on one side, and then by the time it comes to the opposite side, it starts sucking the water out with it. Does that make sense? It's not an easy subject matter. So if you come back to next week and say, Dr. Nolan, I really don't understand, I'll go at it again. Okay? You have to think about it for a while. Okay? Sit there and imagine what this stuff is doing and walk your way through it. There's some... I've never seen a good animation that really does this very well. But some of the Google, some of the new things that they're putting up on iTunes, it's helping a little bit, but sometimes it adds confusion. So if anybody finds anything that would give you a good animation, I would love to see it. Now that I'm learning how to do animation using the PowerPoints, I'm actually beginning to start considering doing this. This one's one of the hardest ones to do animation-wise, I think, so I haven't tried to do it yet, but maybe next semester. I don't know, we'll see. The kidney excretes excess water by forming a dilute urine. So the kidney is able to regulate water excretion independently to solute excretion, which is pretty important. It does by ADH by far. ADH controls urine concentration. It regulates plasma osmolarity and sodium concentration in the plasma. You can remember it's formed by the posterior pituitary. Okay? The posterior pituitary is sensing information, okay? Which then eventually gets down to the posterior pituitary. Okay? What's unique about the posterior pituitary? It is a neural connection between that and the hypothalamus. Okay, thank you. All right. ADH acts by changing the permeability of water in the distal and collecting tubules. It increases in ADH causes an increase in water permeability, and it causes a much more concentrated urine. Now, please, 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 please pay attention to the wording here, because this, every time somebody does not do that, they will get caught in the test. Okay? They just make sure that you get the wording right. If I give you more ADH, I'm going to make a much more concentrated urine and a much more permeable water, permeable tubule. It's going to be permeable to water. On the other hand, if you have decreased ADH, then I'm going to make a much more impermeable or decreased water permeability of the tubule, and I'm going to make the urine more dilute. Okay. Renal mechanisms for excreting a dilute urine. To get rid of excess fluid, urine osmolality must be lower than the plasma. This is achieved by reabsorbing solutes more than water. The tubular fluid remains isoosmotic in the proximal tubule, which you already know that. Then the tubular fluid becomes hyperosmotic as it travels into the medullary area through the loop of Henle. And then the tubular fluid becomes hypoosmotic or dilute in the ascending loop of Henle. And that's irrespective of ADH. Okay? The normal osmolality by the time you get to the distal tubule in the proximal portion of it is around 100 milliosmoles per liter. So that's pretty dilute. You went from 300 down to 100. That's pretty dilute urine. Okay? Now, at this point is when the body decides, should I dilute it or should I concentrate it? If I'm going to plan to keep it diluted, because I'm a person who's getting way too much fluid, then I'm not going to secrete any ADH. Okay? And so really the main mechanism of urine osmolality is ADH. Okay? So without with the absence of ADH, you're going to form a very dilute urine. On the other hand, what happens if you want to concentrate urine? Okay? You can maximally concentrate your urine to about 1,200 to 1,400 milliosmoles per liter. Most of us will do it to 1,200 milliosmoles. Okay? Very few people can reach 1,400 milliosmoles. Okay? Routinely, let's put it that way. Okay? You cannot drink hyperosmolar fluid because it causes dehydration. And you have what's called an obligatory urine volume that you must be removing in your urine, usually around 30 cc's an hour for an adult male. For an adult female, it's around 20 to 25. Requirements for excreting a concentrated urine is high ADH levels and a hyperosmotic renal medulla. In other words, you cannot form a concentrated urine if you've given that person loop diuretics. Because loop diuretics poisons the bucket. You can't concentrate the urine. So if you're giving somebody loop diuretics and then you check their urine concentration and it's dilute and you think, oh well, it's ADH is being secreted not enough. No, it means nothing at that point because you just polluted the whole system with Lasix. Okay? So if you really want to see if ADH is functional or not, you have to do it with a kidney that's not being exposed to loop diuretics. Okay? The countercurrent mechanism is also important as it forms a hyperosmotic renal medullary interstitium, which was I described to you before. How does the kidney generate the hyperosmotic medullary interstitium? It does it by the active sodium chloride transport, by the thick ascending loop of in the nephron into the interstitium. The basically countercurrent system of the blood vessels with the vasa recta, okay, and the recycling of urea between the medullary collecting ducts and the deep portions of the Henle. So those are the three parts. That's what I was talking about. You have to know that. What charges the system? Urea, sodium chloride, potassium pumping from the ascending thick loop of Henle, and the third one is a countercurrent system by the blood vessels. Okay. Again, this is the same picture I was trying to show you. This is somebody who has, let's say you are given a loop diuretic. You poison the mechanism. Okay. Now the system is sort of shut down. Okay. And so as a consequence, you will form very dilute urine. Your urine osmolality will basically fall to basically be equivalent to what's in your plasma, which is 300 in this case. Okay? Now, this individual now is beginning to get return of the sodium chloride pumping mechanism. So it begins to pump sodium out and starts causing the urine to dilute in the ascending portion of the loop of Henle like this. Okay? But at the same time as it's starting to do that, it's beginning to charge up my bucket. Okay? As I put more sodium into it, more sodium begins to fall to the bottom of my bucket. Okay? And that makes you more hyperosmolar at the bottom in comparison to the top. This allows water to rapidly transfer out of the loop of Henle as it travels down the loop of Henle, causing a concentrating effect. So under normal circumstances, you remove about 85% of what you filtered in water by the time you leave the loop of Henle. Okay? The diluting effect that you end up seeing has to do not with water movement, but rather with solute movement. Okay? But really, by the time you leave the loop of Henle, 85% of the volume has been transferred back into the interstitium and back into the blood vessels. And that's important to understand. The role of the distal tubule in the collecting ducts is the ascending loop of Henle. The urine osmolarity is low. Plasma ADH levels are the main regulation mechanism, and water is taken up in the cortex when you add the ADH. Okay? Urea contributes to the hyperosmotic renal medullary interstitium and to a concentrated urine. Okay? If you look at it, it contributes to 40% of the osmolarity in the medullary area. That's a pretty good amount. Okay, so it's a secondary mechanism. The primary mechanism is still going to be what? The sodium chloride pumping. Okay, but the second mechanism, which accounts for 40% of the osmolarity, is urea. And remember, this is passively absorbed in the medullary collecting ducts, or the medullary tubules, and ADH actually increases urea permeability, which kind of helps. I mean, if you think about it, if you're giving somebody ADH, you want to anti-diurese them, wouldn't it also help you make your osmotic gradient even greater, concentrating the urine even more? Yes, and that's what ADH also will do. So ADH has two functions. One, it increases water reabsorption in the distal and the cortical collecting ducts. It also increases water reabsorption in the medullary collecting ducts. But what makes the unique difference is in the medullary collecting ducts, it also increases permeability of urea into the interstitium, which makes the concentration gradient even greater into your bucket, pulling more water out. Okay? Everybody get that? Okay. The countercurrent exchange in the vasa recta preserves the hyperosmolarity of the renal medulla. Without it, if you basically, in other words, kill the blood supply to the renal medulla by impeding the vasa recta vessels, the countercurrent system will basically look like a loop diuretic hit it. Okay? So it's not a good thing. This is a summary. This is what I was talking about, how you need to look at the characteristics of the tubule and what it does in different portions. This is showing you what active sodium chloride transport. The proximal tubule does most of the work in the proximal tubule and the thick ascending loop limb. What's easy to sort of remember is anytime you have a cell that's not thin, that's cuboidal, it's going to pull sodium back across. Okay? So the only ones that don't do it are the thin portions, which is this. Okay? If you look at permeability to water, the ones that are impermeable to water are the thin and thick ascending loops of Henle. The other portions are definitely permeable to water. And then the distal, cortical, and the medullary collecting duct are selectively permeable depending on ADH levels. If I have no ADH, okay, then permeability to water is 0. Okay, if I add ADH, then it becomes permeable to water. Okay? Notice that I keep repeating that over and over again. It's like the fourth time I said it. So you imagine you're going to get a lot of test questions on permeability. Make sure you get that straight in your head. This again shows you the same thing based on the effects of a dilute urine, which is the bottom line, and a concentrated urine, which is the above line. Okay? So look what happens. Look at the differences that you see. Okay? If you want to dilute urine, and what ends up happening is that in the proximal tubule, what does not change? the amount of electrolytes that you're pulling back and the number of solid units you're pulling back is the same. It doesn't matter if you concentrate. So if somebody tells you, can you change the concentration of your urine by changing the proximal tubule? The answer is no. The proximal tubule has not any kind of effect on the sense of diluting or concentrating your urine. Where that effect is, of course, is going to be in the loop of Henle and everything else after that. Okay? Because that's why there's differences in the curves between the two. Right? If you look at the dilute urine, which is the lower curve, you will see that the person doesn't form as much of a concentrated urine. The reason that is because urea is not being excreted into the medullary area in high amounts as much. You're not causing ADH to be secreted, so it doesn't make the area hyperosmotic. Okay, so things like that don't happen. So you end up having a very dilute urine, and then because you have no ADH in the distal and collecting tubules, the urine basically comes out almost in the same quality as when you hit the late distal tubule. Okay, notice that the line doesn't really change all that much. All right, you still lose a little bit of sodium, but not that much. Okay, I mean you don't lose any. Yeah, you pull sodium back in. You pull it back in. If you look at this example, which is the top line, this is a concentrated urine situation. This is when you're severely dehydrated. In this situation, your ADH is being secreted in very, very high amounts, okay? And as a consequence, what happens by the time you get through the loop of Henle, you already have a pretty hyperosmotic, concentrated urine by the time you hit the loop of Henle because of the excessive amounts of urea that's being secreted, as well as concentrating effects inside the bucket that we talked about before. And then you see the diluting segment. It almost comes down to almost the same level. So look at the difference between the distal tubule in the first portion. There's not that much difference. But when you start getting into the late distal, the cortical, and the medullary collecting system, that's where ADH really kicks in. It really kicks in the medullary area. If you look at the medullary area, what happens to concentration? It literally goes to the roof. Okay? And the reason that is because ADH here is extremely powerful, and it pulls more and more water in. And what you end up having is a very concentrated urine by the time you're finished. In this example, you have around 20 cc's of urine formed from 125 cc's that was filtered through. Okay, so 20 is considered dilute, and if you're concentrated, you're down to 0.2. So if you do the math, I don't know if I do the math, it's about 85%. I have to do the math. 20 over 125 divided by, so what's that number? Isn't that about 85? I have to do my calculations. Anyways, you can do that on your own if you want to figure out how much a dilute urine difference is. This accounts for only 20 cc's of 125 that's filtered. That's considered dilute. I mean, but look at concentrated urine. It's only down to 0.2. That's very, very concentrated.